Okay, let's talk about the liquid limit. So the first limit that we're going to discuss, and then the liquid limit has three types of method that you can use for testing. So the first one is the determination of liquid limit by percussion cup method, or sometimes known as the Casagrande. So since it was developed by Casagrande, the equipment for this test. So in this test, this device or the device consists of brass cap and a hard rubber base. The brass cap can be dropped onto the base by a cam operated by a crank, and then to perform the liquid limit test, one must place a soil paste in the cap. So to make a soil paste, you're going to get the sample that you have been sieved from the wet and dry preparation that you choose, and then you mix it with a little bit of water, or you can gradually add some water on it to make it a soil paste, and then you're going to put it in a cup, in the brass cup, and then mix it until it becomes like consistent type or mixture. And then you're going to flatten, and then you use a groove that is used to cut at the center of the soil pot with the standard grooving tool. So by the use of the crank operated cam, the cup is lifted and dropped from a height of 10 mm. So the crank operated cam, or the Casa Grande apparatus, which consists of the brass cap and hard base, can be operated manually or electronically or run by electricity. And then after that, the moisture content in percent required to close at a distance of 12.7 mm along the bottom of the groove after 25 blows is defined as the liquid limit. So right after you you operate, and then when the soil closes, like in the case here, so let's start with this figure. So this is the figure, the profile of the soil paste in the brass cup. So this is the brass cup, this is the brass cup, and this is the cam operated crank, and then this is the hard rubber base. So you're going to operate this one, and then it will lift up and then down, it will drop, and that is what we call the blow. So the soil in here, it has the standard measurement here, of which you have to measure before you do the rotation of the crank. And then that soil paste is also termed as the soil path. So this is the standard grooving tool, and then this is the elevation or the profile of the soil here. So it will follow the groove, the dimension of the groove, that is 11 mm, and then 2 mm at the bottom, and then the depth of the soil path is 8 mm. So this is the top view. You can see here, you will not put the soil path in the full inside, or will not put fully uh, occupied by the soil pot, the inside of the brass. So, and then you can see here the cut, and then you do this is a soil pot before test. You're going to do the blow. After the blow or after the test, you can see it will close. When the soil pot closes at this 12.7 mm in here, you can stop the blowing of the, or the dropping of the brass cap. So at least three tests for the same sample of soil are conducted. So you can test more than three. Three is the standard in experimentation. Three tests for every sample. So you're going to conduct it with a varying moisture contents with the number of blows, that is n. So required to achieve the closure varying between 15. So usually you can drop or operate it, and you're going to count the number of blows. So sometimes it can close at around 15 and 35 and between. So it can be in 21, 20, 28, and anywhere. So you're going to plot every time na nag-close siya. So for example, at first test, it closes at 16. At the second test, it closes around 20. And on the third, it closes at around 28. So you're going to plot that one. So the moisture content of the soil in percent and corresponding number of blows are plotted on a semi-logarithmic graph paper. Okay? So, and then the relationship between the moisture content and the log n is approximated as a straight line. So right after you plotted all the three tests, the result of the three tests, you can plot them in a semi-logarithmic chart and then draw a straight line. And that line is referred to as the flow curve. So you're going to plot from the flow curve the moisture content corresponding to N25 determine the flow curve. So gives the liquid limit of the soil. So this is the actual example of the test. So like this. So this one is the result. So along the x-axis, you can see the number of blows or known as the log scale, and the moisture content along the y-axis in terms of percentage. So you're going to plot at different tests. So for example, you have the number of blows here. For example, this is 16, or that is 16, and then we can estimate the second one is around 22 or 23, and then another test. In this case, one sample, they conducted around 4 tests. So there are 4 samples in here. So we have here example at around 27 or 26, and then in here at around 30, 33, like that example. So you're going to plot that one here, and later you draw a straight line or known as the flow curve. And from this flow curve, you drag a line from the number 25, which is the definition of the liquid limit here, and then you drag going to the y-axis, and whichever value here, no, in tumama siya, that is the liquid limit of the soil. So this is an example of a semi-logarithmic graph. So you can see here, when you say semi-logarithmic, there is a varying distances here. So it can be from longer distance, and then getting less. So you can program this actually in the Excel. And then this is the water content. And then another method for the liquid limit, you can also use this type of graph, but in this case, that is the number of drops. In this case, this is number of blows. So this is an example of the percussion cup method, the result. So example, this is the liquid limit 1 defined at 25. We're going to graph. You can graph here as many samples. You can have soil 3, soil 4, and then just draw from N25. And then you plot in here. So you can see here, sample 1 here, or soil 1, the liquid limit is higher compared to the liquid limit of the second. So these are the different liquid limit test apparatus. So this is the weighing scale, the Casa Grande cup. We have the grooving tool, spatula. This is the mixing dish or the evaporating dish. And the graduated cylinder, you can measure the water, you can put in here. And then this is the water bottle. And then these are the moisture can with lid and tape for labeling. So the slope of the flow line is defined as the flow index. So this, you can compute the flow index, and this is denoted as IF. So that is the moisture content of soil corresponding to N1 blows minus the moisture content corresponding the N2 blows over the log N2 over N1, or the number of blows. So note that the moisture content 1 and 2 are exchanged to yield a positive value even though the slope of the flow line is negative. So thus the equation of the flow can be written in the form like this. So where C is at constant. So from the analysis, this one is the second method known as the 1-point method. So this is from the analysis of hundreds of liquid limit tests. So in the U.S. Army Corps of Engineers, during the time of the 1940s, there are many conducted laboratory tests. So many samples, they use this method. So this was used in the Waterways Experiment Station in Mississippi. So they proposed an empirical equation. When you say empirical equation, these are the equations that were discovered, developed, or created right after a certain research or experiment. So they formulated this one, that is LL equals to moisture content at N, or corresponding moisture content, multiplied by the number of blows, this one, which also follows the Casagrande, Casagrande liquid limit using the brass cup. And then you're going to divide it with the 25, that is the equivalent number of blows that defines LL, raised to tangent beta, that is 0.121. So, but note that the tangent beta is not equal to 0.121 for all soil. So, there is corresponding value for this. So, for routine laboratory tests, it may be used to determine the liquid limit when only one test is run for a soil. So, this procedure is generally referred to as the one-point method and was also adopted by ASTM under the designation D4318. So, the reason that the one-point method yields fairly good results is that small range of moisture content is involved when N equals to 20 to N equals to 30. You can see that later if you do the experiment, that sometimes the difference between the moisture contents of this number of blows is just different. The difference is just at decimal places. Example, 45.20, 45.25, 45.40. So it's just a little small range of moisture content. So these are the values for the N over 25. You can substitute based on the number of blows. So in this case, this is the number of blows from 20, 25, and then 26 to 30. And these are the equivalent values. So another liquid limit, determination of liquid limit is through fall cone method. So in this method, this is under the British standard. If you can notice, the first two follows the ASTM. This one is British standard because British standard is widely recognized also, and widely used. So this is popular in Europe and Asia. So in this test, the liquid limit is defined as the moisture content at which the standard cone of this specification, we have an apex angle 30 degrees and the weight is 0.78 Newton, will penetrate at a distance of d20. So if in Casagrande that is n equals to 25, in this case d is equals to 20 mm in 5 seconds. So when allowed to drop from a position at a point contact with the soil surface. Excuse me. So a semi-logarithmic graph can be plotted with the moisture content versus the penetration D. So, and then the plot results in a straight line. So just like the semi-logarithmic graph used in the Casagrande. So the moisture content corresponding to D20 is the liquid limit or defines the liquid limit. And the flow index can be defined as, so this is another equation for computing the flow index. So that is the IFC equals to the moisture contents at cone penetrations D1 and D2, this one, over the log D2 minus log D1. So this is the example of the full cone test. So this is before, and then this is after, and then the results. There are 4 test example in here, 4 tests for the full cone. So the first result is that the drop or the cone, the fall of the cone is lesser than 20, so maybe around 16 or 17. And then the D here, that is the D here. Okay, there's a measuring here, measurement you can do here. So, and then you plot everything here, and then you draw a straight line or the flow curve, and then at D20 here, D20 with the corresponding moisture content defines the liquid limit. So this is the apparatus for the full cone method. So example of the determining the liquid limit through full cone, we have D20. You just plot the at 20 and then drag going towards the water content. So other computations in terms of LL, these are empirical equations. So as in the case of the percussion cup method or ASTM 4318, attempts have been made to develop the estimation of liquid limit. So these are certain estimations by one point method. So they are this one. We have by Nagaraj and Jayadeva. They formulated this one, an empirical equation, and another is this one. So you may try to use this one or use this one. And then we have by Feng 2001, we have LL. This has something to do with the drop or the fall cone method. So you may use also this one. Okay, for plastic limit, that is PL, ASTM designation D4318, we have certain types of methodology also of conducting the plastic limit. So we have two. The first one is you're going to use the by making a thread from the soil. So the plastic limit in here is defined as the moisture content in percent at which the soil crumbles when rolled into threads. So you can just go back to your childhood days when you play with the soil, and then you get a sample of soil and then roll it or make balls from your palm, and then later you roll it to make something like an elongated soil. So in the plastic limit, if you're going to roll it into threads, and then as it breaks or crumbles, measure it. If it reaches this value, 4.2 mm in diameter, then that defines the plastic limit. So the plastic limit is the lower limit of the plastic stage of the soil. And then the plastic limit is simple and is performed by repeated rollings. So again, at one sample, at least 3. So you can make an ellipsoidal size soil mass by hand on a ground glass plate. So if there's no ground glass plate, you may use a non-porous surface, example tiles. And then the procedure for the plastic limit test is given by ASTM in test designation 4318. So another is the fall cone test for the plastic limit determination. So as in the case of liquid limit determination, the fall cone method can be used to obtain a plastic limit. But there is a variation only in terms of the weight in the specification or the mass of the cone used for the plastic limit. So it's 2.35 Newton, heavier than the liquid limit. So 3 to 4 tests at varying moisture contents of the soils are conducted, and the corresponding cone penetration D are determined. So the moisture content corresponding to a cone penetration of D equals to 20 mm is the plastic limit. So the minimum moisture content at which the soil begins to behave as a plastic is called the plastic limit. So this is the first method. Take a sample. You can also make a soil paste and then you make a ball or you roll it and then roll it later like this. It has a glass in here, a glass surface. And then you may use this one, the equipment. So we have the water bottle, the evaporating dishes for mixing the soil. And then the weighing scale, we have the spatula, we have the moisture can, we have the glass plate here. These are the, just put it at the bottom, no? Some filter paper or some paper. But you cover with the glass. And then you need also a ruler to measure the thread, the diameter of the soil thread. If it didn't reach the certain specific millimeter for crumble, you need to repeat the test. So this is the result example for the full cone method for the plastic limit. So here, that is the moisture content in here versus the cone penetration in here. So these are the four samples for test conducted. And then you plot at D, D20 mm, you drag in here, and you drag at 20 here. That is, this is in terms of the liquid limit. So this first plotting, since the weight of the cone is 0.78 Newton, so you can see here the variation that the moisture content in here is greater. So the second one, the line in dotted line, that is the cone penetration for the plastic limit. So it reaches at 20, so you can see the variation of the moisture content between the liquid limit and the plastic limit. So the plasticity index, we need to compute this one after we have the values for LL and PL. That is the difference between the liquid limit and the plastic limit of the soil. So the equation is PI equals to LL minus PL. So table in here shows the typical values of LL, PL, and activity. So later on, we will have also an equation for activity, where these are for some clay minerals. So these are kaolinite. So these are the typical clay minerals. So these are the values that defines them. For example, at 35 to 100, okay, that is a kaolinite. And 60 to 100, that is an elite. So the clay minerals can be mixture of this, not just one type of mineral. So these are the equivalent PL and the equivalent activity. So for the plastic PI values, so Burmester classified PI in a qualitative manner as follows. So there's a description for every values, computed values for PI. So at 0, okay, non-plastic, and then 1 to 5, slightly plastic. So they have low, and then greater than 40 is a very, very high plasticity. So the plasticity index is important in classifying fine-grained soils. It is fundamental to the Casagrande plasticity chart. So we will also show the plasticity chart later that we're going to use in classification of soil later in the next topics. So this is the typical Casagrande plasticity chart. Plasticity PI here, values of PI, and the values of LL. And then there's a separation in here line, that is the A line and the U line. And these two lines has an equation of equivalent PI. So for U line, that is at this boundary, you have 0.9 times LL minus 8, and A line is 0.7 times LL minus 20. These legends in here, you can see these are the typical types of clays, because this plasticity pertains to clay and silt or fine-grained soil. So you can see here already what type of soil is at this LL, at this LL. Example, we have 80, and then the plasticity index only reaches at 20. So you can say that this soil is inorganic silts of high compressibility in organic clays. So you can define the classification or the type of the soil.